Now let's go to the condenser. So we have the temperature of 37 degrees Celsius. Now looking to the properties table, so we don't have the actual value of your 34 and the actual value of 37 degrees. So from here we need to interpolate the values. Okay, so I bring down here the properties, so I try to zoom that one. So we have in the middle that is 37 degrees Celsius, and we have the corresponding pressure which is unknown, and the enthalpy. This is now in the liquid form since we are touching the saturation liquid or saturation curve. Okay, so this at this point. Okay, so let's try to solve the pressure so that we can plot that one in our pH diagram. So again, just only concentrate on this part rather than on the other part. So let's, in order to find the pressure with the corresponding on the corresponding temperature. So using the calculator, we have the value. We have a value of 1.43. So this is megapascal. Now for the enthalpy, again, so disregard this one. So we'll be using this one. So we have now the enthalpy. So we have the value of 375.87. So the units now is kilojoule per kilogram. Now going to our pH diagram, we have the pressure here, which is 1.43 megapascal. Okay, then we have also the corresponding enthalpy here. So let's try to draw that line to represent that one. So this is now the line that has intersection with the saturation liquid and also the pressure. So that this one will be 300, no? Okay, so this is 375.87. So the units of kilojoule per kilogram. So remembering that from our previous lesson in theories, so we have here a constant enthalpy going to 3 and 4 and 7. So we have a constant expansion from 3 to 4. So if we're going to plot that one, so this one will be a vertical line from the intersection going down to the other points. Okay, so we can also tag this point, that is point 3, and we have here your point 4, and we have also here point 7. And we can also draw the line here, a solid line. So we can draw that one. So that is touching the saturation curve, and also this one touching the saturation curve. And this one will be our 0.5. This is our 0.5, this one. And this one will be our 0.8. This is our 0.8, and this is 5. Next, we need to plot also the 0.6. Now, let's go back to the figure here for the cycle. So you will notice here, this is a pressure reducing valve, and the problem states that we have a back pressure valve. So this is reduces the pressure from 10 degrees evaporator going to -5 degrees. So it means that our pressure here at 0.6 is equal to the pressure at the evaporator at -0.5, -5. So the pressure of the evaporator will be equal also the pressure at this point at 0.6, and this means that it has a constant enthalpy, which is also a vertical line traveling here. So you will notice here, as I will going to zoom, so we have a constant enthalpy from 5 to 6. So since we are going to expand, so this the same also function that we have here, expansion, no? From 3, 4, and 7. So the same process that will be occurring here from 5 to 6, then connecting to point 1. So notice here that I draw a straight line, since the pressure reducing valve is the same also the function of the expansion valve. So I have here now our point 0.6 at this point. Okay, so I will just I draw a thin line here just to represent that one, so that you can also follow. So I have here our 0.6. So this is our 0.6. Now I draw here an arrow to represent, you can easily determine. So this is our 0.6. So we have a constant enthalpy traveling from 0.5 to 0.6. We have an expansion here with the pressure also reducing the pressure at 0.5, the same pressure at the 0.8 or the low temperature evaporator. Now next we need to find the enthalpy at 0.1. So looking at the cycle diagram, so this one at this point, so from here we need to do mass balancing and energy balance to determine the enthalpy at 0.1 and also the mass flow rate at 0.1. Now I try to isolate the mixing T of your 0.6, 8, and 7. Now what we have here, we shall have here the mass flow rate at 0.6 and with the corresponding enthalpy at 0.6. And for 0.8, we will have also the mass flow rate here and the same time also the enthalpy at this point. And this is 0.1. So I'm gonna change this one. This is 0.1. It's 0.1. We have the mass flow rate at 0.1 and we have also the corresponding enthalpy at 0.1. Now for energy balance, we have the energy in, which is your energy out. So we try to only determine the T at this point. So what will be, we'll try to isolate the T here, so to have the energy balance. Now what is entering the T, we have the mass flow rate, no? Mass flow rate at 0.6. So multiply by the enthalpy of 0.6. Then we have also the mass flow rate 0.8, then multiply it by the enthalpy at 0.8. So this is also equal to the mass flow rate at 0.1 multiply the enthalpy at 0.1. Now the values for enthalpy 6, enthalpy 8, we have that value. What we don't have is we don't have the value for enthalpy 1 and the mass flow rate 1. Also mass flow rate 6 and mass flow rate 8. So let's go back to the cycle diagram, remembering that we have also that we can also determine the mass flow rate by means of the change in enthalpy from the refrigerating effect of the evaporator, this one, and also the refrigerating effect of evaporator from 8 to 7. So we can say that our evaporator killing 35 kilowatt, so this is now equal to 35 kilowatt, or let's try to express this one to kilojoule per second. So this is now equal to the mass flow rate at 0.4. Then we shall multiply this by the refrigerating effect of the evaporator, which is your enthalpy at 0.5 minus your enthalpy at 0.4. So we have the mass flow rate at 0.4, then the enthalpy now at 0.5. So we have 1472.11 minus the enthalpy at 0.4. So enthalpy at the 0.4, remembering that we have a constant enthalpy here traveling from point 3 to 4 and 7. So we have the value of 375.87 with the units of kilojoule per kilogram. So let's try to cancel the units here, the common units that we have. So we have your kilojoule. So let's try to cancel that one and this one. So using your calculator, we have the mass flow rate at 0.4 is equal to, we have a value of 0.0319. Okay, so the units is kilogram per second. Now for our mass flow rate at 0.8, so the same process that we shall be doing. So we need to write our equation for the refrigerating effect or refrigerating load of evaporator carrying 70 kilowatt. So we have 70 kilowatt, or let's say this is kilojoule per second. So this is equal to the mass flow rate at 0.7, no? Then multiply with the change in enthalpy at 0.8 to 0.7. So this is now equal to the mass flow rate at 0.7, then multiply enthalpy at 0.8, that will be 1456.66 minus the enthalpy at 0.7. So take note that our enthalpy, no, our enthalpy at 0.3 is equal to 0.4 equal to 0.7. So take note of that one. So we have here 375.87 with the units of kilojoule per kilogram. So let's try to cancel the common units here, kilojoule, and you have your kilojoule. Then we have now the mass flow rate 0.7, which is equal to, so we have the mass flow rate now is equal to, this is 0.0647, or let's say this is 648. We can round that one, round up the values to 8. This is kilogram per second.